Good morning. So, last time we have studied the Thevenize theorem. Today, in this video, we are going to study how to Thevenize a given network. In accordance with the Thevenize theorem, we have seen that any complicated network can be replaced by a simple series circuit consisting of a constant voltage source called as Thevenin voltage source in series with an equivalent resistance called as Thevenin resistance. The value of the Thevenin voltage source is nothing but the open circuit voltage across the terminals A and B, and the equivalent resistance or Thevenin resistance is nothing but the resistance of the given network when viewed backwards from the open terminals A and B, when all the sources of EMFs in the given network have been replaced by their internal resistances. So, let us now study the procedure to Thevenize the given network. So, to understand how to Thevenize a given network or given circuit, let us consider we have this circuit which we want to Thevenize it. Suppose this box contains the given complicated network, and a load resistance RL is connected across the terminals A and B. So we can consider that this network inside this box is connected across the terminals A and B. So, we want to obtain the Thevenin equivalent circuit for this network inside this box. So, the steps to be followed in order to Thevenize the given network or circuit are there are 4 steps to be followed in order to get the Thevenin equivalent circuit for the given network. So, the first step is, step 1 is to remove the load resistance from the terminals A and B. Disconnect RL from A and from the terminals A and B. So, if we remove the load resistance from the terminals A and B, the circuit we get is of this type. These are the terminals A and B. This is the resistance R1, this is R2, and this is the source of point E, this is the point C, and this is the point D. So, once we remove this load resistance from the terminals A and B, we shall the given network will reduce to this point. This is the first step. So, in the first step, we have to just remove the load resistance from the terminals A and B. Now, in the second step, here we want to obtain the values. In order to obtain the Thevenin equivalent circuit, what we need to know is we have to first obtain the value of VTH, and then we have to obtain the value of RTH, and then we can draw the Thevenin equivalent circuit, and by reconnecting the load resistance across the series combination of VTH and RTH, we can find out the current flowing through this load resistance. So here, let us consider that we are interested to find out the current IL flowing through this load resistance RL. So, this is the first step in Thevenizing the given network. Then we have the second step. Step 2 is with terminals A and B open, calculate or measure across A, across the open terminals A and B. So, in order to calculate or measure the open circuit voltage across the terminals A and B, which will give us the value of VOC, the open circuit voltage across the terminals A and B, we must first know what is the current I flowing through this resistance R2. And knowing the current I flowing through this resistance R2, we can find out the potential drop across R2, and this potential drop across R2 is nothing but the potential difference across the points C and D. And since the point C is directly connected to A and point D is directly connected to B, the potential across the points A and B is same as that across the points C and D, and hence this potential across the points A and B is nothing but the open circuit voltage across the terminals A and B, and that will give us the value of VTH. So, in order to find out what is the current flowing through this resistance R2, we can calculate the current I by using the formula I is equal to E upon R1 plus R2. So here, when this load resistance is removed from the points A and B, we have this leftover circuit. So in this circuit, we have a source of EMF E is connected in series with the resistors R1 and R2. And since R1 and R2 are connected in series, so the current flowing through R1 and the current flowing through R2 remains same, and that current is given by this expression I is equal to E upon R1 plus R2. In the given circuit, E is 12 volt divided by R1 is 5 ohm plus R2 is 6 ohm plus the internal resistance of the source is 1 ohm. So this is equal to 12 by 12, so it is equal to 1 ampere. So that the current flowing through this resistance R2 works out to be equal to 1 ampere. So this 5 is the value of R1, 6 is the value of R2, and this 1 is the internal resistance of this source. So that should be taken into consideration while determining the total current I flowing through this resistance R2. So once we know the current flowing through this resistance R2, now the potential difference across R2, ED across R2 is nothing but VCD, that is nothing but VAB, which is nothing but equal to VOC, and this is equal to the product of the current flowing through this resistance R2 multiplied by the value of the resistance R2. So this is equal to I is 1 ampere multiplied by R2 is 6 ohm. So this is equal to 6 ohm. And as per definition, this open circuit voltage across the terminals A and B is nothing but the value of VTH. So VOC or VAB is nothing but equal to VTH, and this is equal to 6 ohm. So we have obtained the value of VTH in this second step. Now, once we obtain the value of VTH, next step what we want to calculate is the equivalent resistance of this circuit. So, in order to find out the equivalent resistance of the circuit, what we have to do is we have to replace the sources of EMFs in the given network by their internal resistances. So, the step 3 is replace source of EMF by its internal resistance. Replace the source of EMF by its internal resistance. So, if we replace the source of EMF by its internal resistance, the network that we will get will be of this type. This is 1 ohm, this is R1, this is R2, and we have the terminals A and B. So this is R1 here, R2 here, and let us discuss small r is the internal resistance of the source. So when we view this network backwards from the open terminals A and B, whatever is the resistance that we observe is nothing but the value of equivalent resistance, and that equivalent resistance is nothing but equal to the Thevenin resistance. So when we view this network backwards from the open terminals A and B, what we observe is that the equivalent resistance of this network is nothing but the parallel combination of R2 and R1 plus small r. So when we view this network backwards from the open terminals A and B, there are two branches. In this first branch we have the resistance R2, and in this second branch we have the series combination of R1 and small r. So equivalent resistance of this network when viewed backwards from the open terminals C and D is nothing but equal to the equivalent resistance of the parallel combination of R2 parallel R1 plus small r. So this is nothing but equal to R1 plus small r into R2 divided by R1 plus small r plus r. The equivalent resistance of the parallel combination is R1 R2 upon R1 plus R2. So using the values of R1 R2 and small r here, what we get is R1 is 5 ohm plus small r is 1 ohm multiplied by R2 is 6 ohm divided by 5 plus 1 plus 6. So this is 36 by 12. So this one is equal to 3 ohm. So R equivalent works out to be equal to 3 ohm, and this R equivalent is nothing but equal to the value of RTH. Thevenin equivalent resistance works out to be equal to 3 ohm. So we have obtained the values of VTH and RTH, and knowing the values of VTH and RTH, now we can replace this complicated network by the Thevenin equivalent circuit. We can replace this complicated network by the Thevenin equivalent circuit consisting of, say, in step 4 is if we replace this complicated network by a series combination of VTH and RTH. This is RTH. So we get the Thevenin equivalent circuit. These are the terminals A and B. So we have this Thevenin equivalent circuit. This is the Thevenin equivalent circuit. So this complicated network inside this box is replaced by a simple series circuit consisting of a constant voltage source in series with an equivalent resistance. So the value of VTH we have calculated is 6 volt, and the value of RTH is 3 ohm. So once we have obtained the values of VTH and RTH, now in the last step, in step 4, what we need to do is we have to find out the current flowing through this load resistance R. We have to find out the current flowing through load resistance R. So the step 4 is reconnect the load resistance RL across the terminals A and B. So we get the network like this. This is RTH, this is VTH. These are the terminals A and B. And if we reconnect the load resistance RL in the circuit again across the terminals A and B, we shall get the equivalent circuit for the given network. And now we can find out the current RL flowing through this load resistance RL. So in this case, the current IL flowing to this load resistance RL will be given by the equation IL is equal to VTH divided by RTH plus R. Because this is a simple series circuit consisting of a constant voltage source VTH in series with an equivalent resistance RTH and the load resistance RL. So the current IL flowing to this load resistance RL will be given by the expression IL equal to VTH upon RTH plus RL. So substitute the values of VTH, RTH and RL. We get VTH is 6 volt divided by RTH is 3 ohm plus RL is 4 ohm. So this is 6 by 7 ampere or IL is equal to 0.85 ampere. So 6 by 7 is nothing but 0.85 amperes. It is 0.85 amperes. So this is how we can find out the current flowing through this load resistance by using the Thevenize theorem. So whenever we want to theorize a given network, we have to follow the procedure in 4 steps. In the first step, we have to just remove the load resistance from the given circuit, and in the second step, we have to find out or calculate the equivalent open circuit voltage across the terminals A and B. And once we calculate that gives the value of VTH. And once we calculate the value of VTH, next step we have to find out the equivalent resistance of the given network when viewed backwards from the open terminals A and B. So that is the third step. And for that purpose, we have to replace this source of EMF by its internal resistance. Kill the source of EMF for its EMF, retaining its internal resistance in the circuit. So we get the value of R equivalent, and that R equivalent is nothing but the value of RTH. So once we obtain the values of VTH and RTH by connecting these two in series, a series combination of VTH and RTH gives us the Thevenin equivalent circuit for the given complicated network. And once we obtain this Thevenin equivalent circuit, in the last step, what we have to do is we have to reconnect the load resistance RL in series with VTH and RTH across the terminals A and B. And we have to find out the current IL flowing through this load resistance RL. So that is obtained by using this formula. So that is the simple procedure to Thevenize a given network. So that is how we can Thevenize the given network. This Thevenin theorem has got certain limitations also. This Thevenin theorem has got certain limitations also. So let us see what are the limitations of Thevenin's theorem. The first limitation of the Thevenin theorem is that it cannot be applied to a non-linear circuit. This Thevenin theorem can be applied only to a linear network, and it cannot be applied to the non-linear circuit or non-linear network. So this is the first limitation of the Thevenin theorem. Secondly, this theorem cannot be used to determine the efficiency of the circuit. Can't be used to determine the efficiency of the circuit. And the third limitation of this Thevenin theorem is that it cannot be applied for calculating the power consumed internally. Can't be applied to determine power consumed internally. That is, in the internal circuit, how much power is consumed, that we cannot calculate, but it gives power in low resistance. Correct. It gives the power in the low resistance very accurate. So though it gives the power across the low resistance correctly, it cannot be used to find out how much power is consumed by the internal circuit. So these are certain limitations of the Thevenin's theorem. So we'll close it here for this video, and in the next video we shall study the normal theorem. Okay, thank you.